This is the second part of the endocrine system. Remember, the objectives for this part are also located at the beginning of the first endocrine system part. The thyroid hormones are called T3 and T4, or the longer names are triiodothyronine and thyroxine. You can see why we like to call them T3 and T4. Both of these are produced by the thyroid gland. I'd like you to look at the word triiodothyronine. That word tells you something. First of all, tri tells you that the molecule has three of a particular entity, and that entity is iodine. So iodo tells you that iodine is present in T3 and T4 hormones. This is going to have implications for one of the diseases that will be discussed here in a few moments. T3 and T4 are known as, quote-unquote, the thyroid hormones, but the thyroid gland actually produces another hormone. It's called calcitonin. Calcitonin is important, and we will talk about it, but it's involved in calcium regulation. T3 and T4 are similar hormones, and both of them are more metabolic in nature. They affect the basal metabolic rate of the cells, and they have an impact on metabolism in several types of ways, most notably in protein synthesis. So we will talk about that here in just a moment. But I need to get back to the middle paragraph where it says that T3 and T4 are called the thyroid hormones. You know how sometimes a term will be used and it may not quite make sense, but it's just the way it's used? In everyday language, if someone has to take thyroid hormones, they're not talking about calcitonin. The doctor is going to put them on a synthetic or even a natural type of hormone, which will be identical or similar to T3 and T4, not calcitonin. So they are just called the thyroid hormones, even though calcitonin comes from the thyroid. So having said all of that, to reiterate that T3 and T4 regulate the basal rate at which the cells metabolize nutrients, most notably protein synthesis. They are absolutely required for the cell to make proteins. T3 and T4 have several other effects, including sensitization of the heart muscle, the myocardium, to the effects of other hormones, including epinephrine and norepinephrine. And we'll talk about epinephrine and norepinephrine later as well. This slide will look familiar to you, except this time it's illustrating the relationship between thyroid stimulating hormone, T3 and T4, and protein synthesis. So if you look at the first box there on the left, the anterior pituitary releases a hormone, tropic hormone. In this case, it's TSH. That hormone travels through the blood to the target gland, in this case the thyroid gland, causing it to release its hormones, T3 and T4, which would be H2 in this instance. T3 and T4 travel through the blood to the secondary target cell, which specifically in this particular instance is going to cause cells of the body to increase the manufacture of proteins. So the word synthesis means to manufacture. The thyroid gland is located in the neck. It's below what we call the Adam's apple, which is the medical name for that is a cartilage. It's called the thyroid cartilage of the larynx or voice box. This slide shows the relationship between the hypothalamus, the anterior pituitary, and the thyroid gland. The hypothalamus releases a hormone called thyrotropin releasing hormone, which is going to actually control the anterior pituitary. We saw this on a previous slide as well, in which the hypothalamus was shown having an effect on the pituitary. So for each of the hormones from the anterior pituitary, the hypothalamus releases a a releasing hormone, or secretes a releasing hormone that will tell the anterior pituitary what to do or when to release its hormone. So thyrotropin releasing hormone works on the anterior pituitary, causing it to release TSH, or thyroid stimulating hormone. TSH travels through the blood to the thyroid gland, which is represented by the little orange box at the bottom there. When TSH stimulates the thyroid gland, the thyroid will grow, and you can see the arrow on the left indicates the thyroid is growing, and it will secrete one of its hormones, T4 or thyroxine. Thyroxine will have the positive effect on metabolism of the cells, but if it increases in concentration above a certain point, it will cause a negative feedback reaction, which will cause the anterior pituitary to stop releasing TSH. Classic negative feedback. Disorders of the thyroid gland, similar to other endocrine disorders, can be either ones of hyposecretion or hypersecretion. Hypothyroidism, just like it sounds, is a condition in which too little thyroid hormone is produced. The symptoms of hypothyroidism are weight gain, fatigue, and cold intolerance. It's a fairly common condition, but not as common as hyperthyroidism, in which too much thyroid hormones, T3 and T4, are produced. In hyperthyroidism, there's weight loss, anxiety, heat intolerance, and abnormal heart rhythm. If you think about what I said a moment ago about T3 and T4 making the myocardium, the heart muscle, more sensitive to certain other hormones, that's what we're talking about here. Too much thyroid hormone release will cause the heart to be way too sensitive to the normal hormones that affect it, that control it, and so it will cause greatly increased heart rates and certain conditions that we called arrhythmias. Another condition is called the goiter. A goiter is a nonspecific symptom, really. It's an enlarged thyroid gland, but basically it can be due to either hyperthyroidism or hypothyroidism. Another condition involving the thyroid gland occurs in the fetus and in little infants less than 6 months of age. It's due to insufficient secretion of T3 and T4 in that little individual. And the reason they don't secrete enough T3 and T4 is due to iodine deficiency, either in intrauterine life before birth or shortly after birth. The big problem with cretinism, it's not just hypothyroidism. It's not like you can do anything about it. Once the child has passed that critical time point, certain things have occurred in the form of physical and mental development. Certain abnormalities have occurred that cannot be reversed, no matter how much thyroid hormone is released after that. So you see, the brain is developing not only after birth, but all the way up until an individual is an adolescent, and it's believed even into early adulthood. The quickest or the most rapid degree of brain development, though, is in the young child, and so thyroid hormones, T3 and T4, are necessary for the cells to produce proteins, and the development of the central nervous system is so critically dependent on protein synthesis. Not only are there mental delays, however, or not delays, but abnormalities, but there are also physical impairments as well. And so, like I said, this is a permanent condition. It's not, you can't treat it. You can prevent it by making sure the mother has enough iodine, but you can't treat it once it's happened. Other hormones include calcitonin and PTH, or a parathyroid hormone. Calcitonin, you may recall, I just mentioned that a moment ago. Calcitonin is another hormone from the thyroid gland, whereas parathyroid hormone comes from a gland or several glands by the same name, the parathyroid hormones. Both of these hormones regulate calcium in the blood. These are what we call counter-regulatory hormones. That word will be provided in part 3 of this series, but because there are several sets of hormones that are counter-regulatory. But what that means is if two hormones are counter-regulatory, it means that if one of them increases a function or a level or what have you, the other one is going to have the opposite effect. It's going to decrease it. So calcitonin and PTH have opposite effects on the concentration of calcium in the blood. Calcitonin decreases the blood calcium concentration, while parathyroid hormone, or PTH, increases it. I like to remember, and in fact I have to think about this, or sometimes I won't be able to remember which hormone does what. Calcitonin decreases the concentration of calcium in the blood, and the way I remember it is I think of a father telling his daughter, to turn the music down, saying, tone it down in there. I guess daddies still do that. They did it when I was a teenager. But at any rate, to tone it down, if a parent's telling you to tone something down, they mean to be quiet or to, behave yourself or something. So calcitonin then is going to decrease the calcium in the blood. It's going to tone it down. Then you can remember that the other hormone, PTH, is going to have the opposite effect. It's going to increase it. These hormones affect several tissues, especially parathyroid hormone. Both of the hormones do affect the bone, and that's primarily the site of the calcitonin, while parathyroid hormone affects the kidneys and indirectly also affects the intestines. So if we talk about what the two hormones do to the bone, and you have to think about this carefully now. You know what the hormones do to calcium in the blood, but now we're talking about what do the hormones do to the bone itself. Calcitonin decreases calcium in the blood by causing calcium to enter the bone, so that calcium comes out of the blood and goes into the bone. Parathyroid hormone increases the calcium concentration in the blood. Where does it get the calcium? Out of the bone, you see. So calcitonin causes the bone to take up calcium. Parathyroid hormone causes the bone to release calcium. I thought it was important to tell you different processes in the body that require calcium, because I don't think any discussion of parathyroid hormone and calcitonin would make very much sense if you didn't really know why calcium is important. The obvious reason we need calcium would be for proper bone strength. You know that if you don't have enough calcium in the bone, then you could develop fractures, breaks of bones very easily. So you need it for strong bones. You need calcium for muscle contraction. Muscles will not contract without calcium. For nerve impulse conduction to take place, for neurotransmitters to be released, you need calcium. Blood will not clot in the absence of calcium. Enzymes, hormones, incidentally, certain other compounds like growth factors that are secreted by cells will not occur. The secretion will not occur if calcium is not present. And then finally, calcium acts within the cell as what we call a second messenger to allow one cell to communicate with another. Vitamin D is discussed when we talk about parathyroid hormone. You'll see why here in just a moment. First of all, I need to tell you that vitamin D is not only a vitamin, but it is also a hormone. Vitamin D is produced in the body it travels through the blood to its site of action. That makes it a hormone right there. It's a vitamin, though, because it also occurs in foods, and so when we eat the particular food or drink the beverages that are rich in vitamin D, it's a vitamin that in that case, because it's coming out of the environment, I guess you could say, into the body. So it's a vitamin and it's a hormone. Vitamin D is a steroid hormone. It is needed for proper calcium absorption from foods. So remember what we said about PTH, parathyroid hormone. Parathyroid hormone is necessary for the absorption of vitamin D. Okay, but vitamin D is necessary for the absorption of calcium. You could drink milk, eat ice cream, pudding, yogurt, cheese. I'm naming a lot of foods fortified in vitamin D right now. You could eat all of these things every day and get 3 times the amount that you normally would need, and yet you would still be calcium deficient if you didn't have vitamin D as well. Now, it turns out that those foods I just mentioned, they usually are going to have vitamin D in them, not because they occur naturally that way, but because any dairy product, including milk, that you buy in a store will have been processed or fortified with vitamin D. The reason for that is that we have very few sources of natural sources of vitamin D in our foods as a rule. Egg yolks have vitamin D. Beef and liver and certain kinds of fish have vitamin D. But that's about it, a few of the vegetables. So luckily, vitamin D is put into the milk and the dairy products. But I mentioned the fact that your body produces vitamin D. It has been widely reported, and I've taught it for years as well, that if you get a few moments of sunshine every day, you can produce enough vitamin D for your own needs, I don't know if I was told incorrectly or more information came in. I'm not sure exactly when this became no longer the case, but all of a sudden, for many, many people in this country and even more people abroad, we're not getting enough sunlight to produce enough vitamin D. So we're going to look at that in the next slide. Vitamin D deficiency is a big health problem worldwide and even in our own country. In the U.S., there's an overall incidence of about 42%. 42% of the individuals in our country are vitamin D deficient. In African Americans, that's doubled. It's over 80% of African Americans are vitamin D deficient. This is a huge health problem, or it can be, if that deficiency persists. It's not just strong bones either. Vitamin D has a lot of other secondary functions in the body that you might not have even been aware of. So I wanted to reiterate something, that sunlight is you could say, a source of vitamin D. It's actually a catalyst that catalyzes the reactions in the skin that lead to vitamin D. But so most of us don't really get enough sunlight. So therefore, different foods that are rich in vitamin D include fish, and it's not just any kind of fish. It's not catfish. It's not trout or anything like that. It's basically, actually some trout probably would have vitamin D, but salmon, tuna, swordfish, and sardines are types of fish that are high in vitamin D. Liver and beef meat has vitamin D in it. Liver is a good source of it. Egg yolks are a good source of vitamin D. And then these different foods that are fortified with vitamin D. Look at the last one on the right, ready-to-eat cereal. Many of our cereals are fortified with vitamin D as well. So apparently we're still not eating enough of the foods that contain vitamin D. There are diseases then caused by vitamin D deficiency. And I'm only going to talk about diseases that do affect the bone. Like I said, there's a whole host of other diseases. It's believed that vitamin D deficiency can enhance the chances of getting certain kinds of cancer. It can enhance the chance of causing prostate problems. Lots of other deficiencies as well, or abnormalities as well. But with regard to the skeletal system, a lack of vitamin D or deficiency of vitamin D can cause a disease called rickets. In children, the disease is called rickets. The same problem in adults has a different name called osteomalacia. So in children, rickets then is a disease in which the bones are too soft. When the baby begins to stand up and start pulling up on things and getting ready to walk, the little legs will just bow out. The legs cannot support the weight of the child, and so severe bow-leggedness occurs. Bow-leggedness is not just an aesthetic problem. In other words, it's not just because you don't want to see that because it doesn't look nice or it doesn't look attractive or something. It's a lot more important than that. It has a lot of repercussions there, so you want that to be corrected. Other bones can be malformed, not just the legs as well. Osteomalacia is caused by vitamin D deficiency in adults. And it's kind of like osteoporosis, except that osteoporosis is due to estrogen deficiency in women or testosterone deficiency in men, whereas osteomalacia is due to vitamin D deficiency. Except for that, the diseases are actually quite similar. The main problem with osteomalacia is that it causes bone fractures, which is the same thing as breaking of the bones. Another vitamin I wanted to talk about is called vitamin C. It is vitamin C. Vitamin C is not a hormone at all. The body can't produce vitamin C. However, it is a vitamin that's necessary for proper bone strength and bone health, and so we usually discuss it when we talk about vitamin D. Vitamin C is necessary not only for healthy bone, but for other connective tissue health as well. You see, bone is a connective tissue. The tie-in between vitamin C and connective tissue is a protein called collagen. Collagen is a type of fiber that strengthens connective tissues. If collagen is weak, the connective tissue will be weak as well, and a lot of different problems can result, including bone fractures. The bones will be very brittle. If a person is vitamin C deficient, instead of the bones being soft like they were with the vitamin D abnormality, with vitamin C deficiency, the bones are very brittle and will break very easily. One of the diseases caused by vitamin C deficiency is called scurvy. So I'll go to the next slide and look at that. You may have heard of scurvy before, and in the context possibly of learning about explorers when they came to the New World way back in the 13th, make that 15th, 16th centuries, I think. But the explorers came over. They were on the ships for several months, and a lot of the time many sailors didn't survive the trip. A lot of them would develop sores, open sores in the skin. Some of them would break bones without very much effort, actually. A lot of them, their teeth would begin to decay. The teeth would begin to fall out. The common denominator among all of these problems turned out to be a lack of vitamin C, and so therefore the collagen was not strong enough to maintain the bone health and the tissue health. And you may recall the rest of the story, and that is that when they began to start taking citrus fruit, such as limes, on the ships with them, that's when the scurvy stopped. And all of a sudden, the sailors recovered, and they were able to, withstand the trip really well. So, but you don't have to be an old world sailor to develop scurvy. Scurvy even occurs in these days and times. Now we'll go on to another type of hormone. These are hormones produced by the adrenal glands. The adrenal glands are glands that sit atop the kidneys, above the kidneys. The word adrenal, AD, means towards or to. Renal has to do with the kidneys. So adrenal glands sit next to the kidneys, I guess you could say, basically above the kidneys. Like I said earlier, the adrenal gland consists of two different parts, the adrenal cortex and the adrenal medulla. So we're going to look first at the hormones of the adrenal cortex. One of these is called aldosterone. Aldosterone is a steroid hormone. It is, of course, secreted by the adrenal cortex. It travels through the blood to its target organs, which are the kidneys. The effects of aldosterone are that aldosterone stimulates sodium reabsorption by the kidney. Therefore, less sodium is excreted in the urine, more sodium is retained in the blood. Now you may know this little maxim that if you retain sodium, you're going to retain fluid as a result of that. So if you retain sodium in the blood, more water is going to be held in the blood as well. So there will be less urination and the blood pressure is going to increase. It turns out that aldosterone is a major factor involved in maintaining the blood pressure. By maintaining blood pressure, I mean that if something occurs to make the blood pressure drop before normal, it's brought back up to normal by largely by the action of aldosterone through what we call the renin-angiotensin-aldosterone system. Sorry. This is a familiar slide by now. It shows the anterior pituitary that is going to signal its target gland to release hormones. So let's look and see the specifics. The tropic hormone number 1 comes from the anterior pituitary. This hormone is called ACTH, or adrenocorticotropic hormone. This hormone travels through the blood to its primary target gland, which is the adrenal cortex, causing it to release hormone 2, or aldosterone. Aldosterone travels through the blood to the secondary target gland, which would be the kidneys in this case, causing a further effect on the kidneys, this effect being reabsorption of sodium and therefore conservation of water in the blood. Now you may think that I'm going to tell you that the main stimulus for aldosterone secretion is ACTH. And ACTH is a stimulus. If you look on the second line, the second bullet point, it tells us ACTH is a stimulus for secretion of aldosterone, but it's not the main stimulus. The main stimulus is another hormone called angiotensin II. I'm looking at the third bullet point now. Angiotensin II is a hormone that is formed when blood pressure decreases below its set point. When the blood pressure drops, one moment. When the blood pressure drops below normal, or we say below the set point, the kidneys will detect this and will release a hormone, an enzyme, that is going to bring everything back to normal again. The details of this will be shown on the next slide. So, if the blood pressure drops below normal, the kidneys release an enzyme called renin. Renin is going to cause angiotensin II to be produced, and the effects of angiotensin II are very many and varied, 7 or 8 at least. I've listed 3 right here. One of the effects of angiotensin II is aldosterone secretion. Another one, the next bullet point, peripheral vasoconstriction. The third one, stimulation of thirst centers in the hypothalamus. So let's look at what aldosterone secretion is going to do. This is going to sound familiar to you at this point because angiotensin II is going to stimulate the adrenal cortex to release aldosterone. Aldosterone will work on the kidneys, causing them to conserve sodium, to conserve water. Both of these entities will increase in concentration in the blood. This will bring the blood pressure, the blood volume up, and will bring the blood pressure back to normal. If you look at the second one, peripheral vasoconstriction, that means that blood vessels in the skin and the mucosa will become more narrow in diameter. This is going to also increase blood pressure. The third bullet point, angiotensin II causes the hypothalamus to activate the thirst response, causing the person to drink more water, which will increase the blood volume, which will increase the blood pressure. So angiotensin II is the most potent substance produced by the body that can raise the blood pressure, and there are many different hormones and other chemicals in the body that can increase blood pressure, but angiotensin II is the most potent one. This slide is going to reiterate what I told you just a moment ago about aldosterone and angiotensin II, but hopefully it's going to be a little bit more meaningful to you. What we want to do first is look at the two red boxes towards the right side of the slide. Look at the bottom one first. It says that there's a drop in blood pressure that occurs specifically in certain arteries or arterioles of the kidney. This could be due to bleeding. An individual is bleeding, they lose a significant amount of blood, or it could be due to any number of other things that could cause the blood pressure to drop, like certain medications that person may have taken, lots of other things like certain diseases that can cause the blood pressure to drop. So if the blood pressure drops below the set point within the kidneys will release an enzyme called renin. So follow the yellow-colored, neon kind of yellow-colored arrow going to the left from the red box and upward to renin. Renin is an enzyme that is going to convert a substance called angiotensinogen to angiotensin I. Angiotensin I will then be converted in another reaction to angiotensin II. Notice that angiotensinogen is converted to angiotensin I. Angiotensinogen is produced by the liver, and it's circulating in the blood. It's only activated, though, when renin is released, and renin is released only when the blood pressure has dropped below normal. Okay, so let's go back to angiotensin II. This is one of the three boxes, green boxes, that has the hot pink writing in it, angiotensin II, on your left. As I said a moment ago, angiotensin II has several effects. Let's look at some of these. If you look at angiotensin II going to the left and then upward, notice that angiotensin II increases sympathetic nervous system stimulation. That in itself can cause the blood pressure to go up by many different mechanisms. Okay, so that's one way that angiotensin II can increase blood pressure. Look on the opposite side of the box, angiotensin II. Notice the arrow that goes downward and then across and upward. Angiotensin II can increase the constriction of blood vessels in the periphery, the skin, like I said before. That's going to raise blood pressure. But look at the main mechanism of angiotensin II. This is a center arrow. Angiotensin II is going to cause the adrenal cortex to release aldosterone. That's another green box with the pink writing in it. I've got three hormones listed in pink. That's why they're pink. So aldosterone is released because of the effect of angiotensin II on the adrenal gland. Aldosterone, follow the arrow upward from aldosterone, increases sodium reabsorption or conservation by the kidney. Go towards the right, seeing that that's going to cause the kidneys to lose less water. This means more water is going to stay in the blood. That's where it says plasma water content increases. More water stays in the blood. That increases the blood volume. That's going to increase something called the stroke volume, which increases the amount of blood pumped per minute by the left ventricle or the cardiac output. And finally, that is going to increase the blood pressure. I didn't mean to overwhelm you with such a busy slide, but I think that it helps to see just how complex certain metabolic or actually physiological processes can be inside the body. So you can see all of the interplay between aldosterone and angiotensin II, sodium and water, and so on and so forth. I wanted to show you one other hormone. We've already looked at it, antidiuretic hormone. The other pink writing in the box there, that one came from the hypothalamus and the posterior pituitary. Antidiuretic hormone also works on the kidneys, causing them to conserve water, but it acts at a different place than what the aldosterone does. But you can see that antidiuretic hormone and aldosterone, are going to lead to some of the same effects, meaning an increase in water in the blood, increased blood volume, and blood pressure.